Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is the magnetic force on moving charges. Now we've already covered some of the basic physics that you need to understand this. If you go back to the last video, the one that was shared with grade 11s and 12s, where we talked about right-hand rule number 3, the motor principle, we learned that there is a force exerted on a conducting wire that has current moving through it if it is in the presence of some other external magnetic field. Well, in this video, we're going to look at the force on the individual charges that make up that current, and in doing so, we're going to get to some really neat applications of this idea. That's called the mass spectrometer and the charge-to-mass ratio. So I think you'll enjoy this video, especially if you're going to be going into anything physics or chemistry related. You'll probably have an opportunity in university to use this device called a mass spectrometer. Anyway, without further ado, just take a moment to pause the video, have a look at the where we are in the homework schedule and also what the learning goals and success criteria are, and then come back and we'll get started. Okay, you're back and here we go. So first of all, just to review a little bit, what we were learning in the previous video was that if you have, let's say, a wire which is situated in a magnetic field, as shown by this diagram here, and you have a current running through it, the external magnetic field, represented by the north and south ends of these two magnets, it will interact with the magnetic field due to the current in the wire, and you will, of course, get either attraction or repulsion. There will be a force exerted on the wire. We use our right hand, which is opened up like this so that you can see the palm of the hand. The fingers line up with the magnetic field, which is from north to south. The current is the direction that your thumb is pointing, which in this case would be to the right, and if you realize here, your fingers would be into the page or pointed toward the screen of your computer. This diagram, which is drawn in perspective, the magnetic field is actually shown as X's with circles around it. That's the B, or magnetic field, and therefore the palm of your hand, your right hand, should be pointing up. That's the direction of the force. So this wire is going to be forced up, and a nice demonstration of this is if you've ever seen a very simple cathode ray tube. Maybe you've seen this demonstrated. You can certainly go on YouTube and take a look. We have an evacuated chamber in here, a vacuum chamber, with two electrodes. They're connected to opposite terminals of a high voltage power supply, and if you have a sufficient voltage, a beam of electrons will move from the cathode to the anode, and there will be a glowing, they will give off a glow as they collide with a few of the molecules that are left in the chamber. And if you bring a magnet, which is what is here, near that beam, you will actually see the beam get deflected. So this is showing that a magnetic field from the external magnet can exert forces on moving electric charges. Of course, magnets don't exert forces on stationary electric charges. To get an idea of this, all you need to do is take a magnet and bring it near various different kinds of metals. For example, bring it near an aluminum can, like a can of Coke or something. It will not lift up the can. The can, which is made of aluminum, is not a ferromagnetic substance like iron is, so you'll get nothing. Of course, it will pick up some substances like iron. You know, you could pick up, let's say, a quarter or a nickel, which contains steel, which contains iron. But that does not happen in every substance. However, if the charges are moving, it's a different story. We need moving charges. We need current to generate that force. So, by the way, just before I forget to mention, this video is off of Google, or this image here is off of Google Images, and this one is out of the grade 11 physics textbook, Physics 11 by Addison Wesley. Anyhow, getting back to what I wanted to discuss here is, now that you understand that forces are being exerted on each of the individual charges that are moving in this conductor, we now need to look at the formula that tells us how much force is exerted on each of those charges. The idea being, if each of the little charges that's moving through this conductor experiences a little bit of force, then if we add up all those forces, we get the total force on the wire. So if you read in your textbook, or if you do a little bit of research online, you'll find that the formula for the magnetic force exerted on a charge depends on a number of variables, and I'd like you to pause the video right now and try to brainstorm what factors do you think would affect how much force each individual charge in this conductor is experiencing? And then come back. All right, you're back, and what did you come up with? Well, hopefully you realized that the greater the magnetic field over here, the greater the force. So we should see the letter B in this formula. And I think we're ready now for the grade 12s to introduce, for magnetic field, what are the units? Because we haven't really talked about that. The units of magnetic field are the Tesla, symbol T, and there's also a smaller unit called the Gauss, which is given, I believe, the symbol G. You might have to check that out for me. I'm not 100% sure for one time in these videos. Just so you know, there are 10,000 Gauss, I'll give it the letter G right now, for 1 Tesla. And just for reference, you may be wondering, how strong is a Tesla? Is that a lot? Is it a little? Actually, a Tesla magnetic field is extremely strong. There are very few magnetic fields that we encounter on a regular basis that have a strength of 1 Tesla. The Earth's magnetic field is probably the one you're most familiar with. It is what allows you to navigate with a compass. And the Earth's magnetic field, so we could write this as B for Earth, is about half of a Gauss, which would make it only a tiny fraction of a Tesla. So that just gives you some reference. And if you were to take a bar magnet, let's say, like they're representing here, of course a bar magnet can easily manipulate the needle of a compass much more effectively than the Earth's magnetic field. So we would know that a bar magnetic field is actually much stronger than the Earth's magnetic field, just to give you some reference. And if you want to go looking up on the internet, you can see what are the ranges of magnetic fields. Probably the strongest that you're ever likely to encounter, and this would only be if you needed certain medical procedures, would be in an MRI machine. Why don't you go look up right now, what is the magnetic field due to a magnetic resonance imaging machine? For those of you going on into medicine, this will be of interest to you. But anyway, getting right back to how we got off on that little tangent, we were looking at what is the magnetic force on each of the charges that moves through this wire when it is in a magnetic field. That should depend on the strength of the magnetic field, and it does. What else does it depend on? Well, if you have been in class and paying attention, by this point we would have done a demonstration of this effect, the motor principle as it's called. And what you would have seen me do in the demo is take the current, symbol I, and increase it and decrease it. And you would have noticed that as I increase the current, I get more force. And as I decrease the current, I get less force. So you would expect there to be the letter I in here. However, current is made up of many, many, many charges that are flowing. If you recall from grade 11, I, the current, is the amount of charge flowing, Q, past a certain point in the circuit divided by the time taken. So there is the idea of charge in there. So we don't really want the letter I in here because that deals with many charges, and what I'm trying to figure out is the formula here for the force on one charge. So there will be the letter Q in there for a single charge, and this will of course be in coulombs. So we look at the charge that is moving through the magnetic field, but we also have the idea that it's got to flow and move in time. So what ends up coming into this formula is V, not as in voltage, but as in speed. That's where we get the idea of current coming in here. All right, so this will be in meters per second. And pretty much this is the formula for the magnetic force on the charges that are moving through the magnetic field. Now, there is another term in here, and that is a sine of theta. This is what you may not have guessed, where theta is the angle between B/W, between the velocity and the magnetic field. So if you go to this example here, this diagram that they drew in the grade 11 book, you see the current and therefore the velocity is moving to the right. And the magnetic field they've drawn it in perspective. It's supposed to be in to the page. I've shown that with an X and a circle around it. And so the angle between these two would be 90 degrees. So when you plug that in here, you'll get the sine of 90, which is equal to 1. Now, if the angle were anything less than 90, the force would actually diminish, and it would actually reach 0 in the case where the magnetic field and the velocity are parallel to one another. All right? Now, how can I show this to you? If you're watching, I'll probably have shown this to you in my demonstration in class. What I'll do is reorient the magnet and the wire so that they are parallel to one another, and you'll see that there is no force exerted on the wire. Okay? Now, for those of you who've taken vectors and calculus, you will have studied a type of vector multiplication which is called the cross product, or the vector product. And this is only for the students who've completed this. For the rest of you, don't worry too much. You'll learn about it when you do calculus and vectors. But what you guys will have seen is that the force is equal to the charge times the velocity crossed with the magnetic field. So this is how the calculus and vectors people will recognize it. This is a right-hand rule it's a calculation involving right-hand rule, where you will get the magnitude of a cross product being equal to the magnitude of the individual vectors multiplied times the sine of the angle between them. And the direction, of course, you do the right-hand rule. You do what's called a curl. For those of you who have no idea what I'm talking about because you haven't taken grade 12 calculus and vectors, all you got to do is remember that this formula gives you the magnitude of the magnetic force, and the direction is given by right-hand rule number 3, which we've already learned. There's just one catch. Remember, right-hand rule is for positive current flow. That's the way we look at current in the conventional sense. Even though we know that in an electric circuit it's the electrons are moving, remember that most professionals look at current as the direction of flow from the positive terminal to the negative terminal. So it's the direction of, quote, positive flow. What do you think would happen if we actually did have electrons moving through here? In that case, the force direction would be reversed. All right? So when you are doing the direction here, you better be very careful to notice that this is for positive flow. If you're dealing with negative charges, you're still going to use QVB sine theta. However, you are going to reverse the direction of the force that you get when you do the right-hand rule. Or some people use a left-hand rule. But since we've been using the right-hand rule, we're going to stick with that. We're not going to get into the right-hand rule. Okay? And anyway, that is, by the way, the fact of the video. Being able to use the right-hand rule and this new formula, QVB sine theta, to determine the force on an individual charge moving through a magnetic field. All right, so let's actually now start to take a look at what happens when a charge does enter a magnetic field, something that you will remember from the past. We end up with uniform circular motion. Let's see how it works. You've got a charge here, which is a little hard to see, but the idea is to think of a charge as existing, let's say, right here. So this is the charge, and we're going to call it Q. And it's also got a mass, which we will use the letter M to designate. Suppose the charge is moving in this direction. All right, so let's just call this a velocity to the right. And let's assume that it is a positive charge, just to keep things simple for now. You're given two magnets. The north end of the magnet is up here, and the south end is down there, which means that the magnetic field, as they've shown, is pointing down. So what I'd like you to do, just for this charge right over here, I want you to pause the video in a moment and use the right-hand rule, all right, the right-hand rule being this, to predict the direction of force on this charge. Okay, pause the video and do that now, and then come back. All right, you're back, and let's see what you got. If you did this right, then your fingers should be pointing down in your right hand. Your thumb should be in the direction of velocity because that would be the direction of current. And therefore, your palm should be pointing in to the picture or into the computer screen. And therefore, we would show that as an X with a circle around it. The direction we would say is into the screen. We also might say that it is away from us. These are all words that can be used to describe the force direction. And if you repeat this for all the different positions that they've drawn particles in this diagram, you can check to see that the force direction keeps pointing in what I would describe as an inward direction. And because the force is always perpendicular to velocity, guess what? You have a situation that is described by uniform circular motion, where the force is perpendicular to velocity and it's constant, so the acceleration is constant. We've got uniform circular motion here. So let's see what we can write. If the magnetic force is equal to the centripetal force, then we can write QVB sine theta equals mv squared over r. There's a v here, and there is a v there, so that's going to cancel. And now there's a number of ways you can rearrange this, but what I like to do is rearrange for the radius, because this is telling me that the radius of a circular path taken by a charge moving through a magnetic field will be equal to the mass of the particle times its speed divided by the magnetic field strength that it's in, the charge, and actually let me just write that. Let me write the Q first, and you'll see why in a minute. The charge times the magnetic field times the sine of the angle between the magnetic field and the velocity. Now, quite often you'll notice in the problems that theta's 90 degrees. And therefore, the sine of theta will be equal to 1. What we end up with is r equals m over q v over b. All right? This is giving you the radius of the curved path taken, and of course, let's think about this formula for a minute. Does it make any sense? Let's look at the letter v. This is in the numerator, so it's telling you that as you increase the speed of the particle, you increase the radius of the circle it makes. Does this make sense? Sure, it makes sense. It's like you trying to drive your car in a circle, or ride your bike in a circle, or run in a circle. The faster you're going, the larger the radius. On the other hand, the magnetic field is in the denominator. If you increase the magnetic field, what's going to happen? Well, you're going to exert more force on the particle, so the radius of the turn will decrease. That makes sense. All right, so the formula does make sense in those respects. How about the mass here? Just use a different color and you'll see why in a minute. The mass, as we increase the mass of the particle, it has more inertia. It's harder and harder to get that particle to move in a circle, so the radius increases. On the other hand, as the charge increases, more force is exerted because of QVB sine theta. So if you increase the charge, you get a smaller radius because more force is being exerted. So the formula makes sense, and the neat thing is that if you take these two terms, the mass and the charge, we can actually define something that is called a m over q. I guess you would call that as a ratio. It would be a mass to charge ratio. Or if you flip that upside down, q over m, you get the charge to mass ratio. And because every particle has its own mass, I don't think there are any two different particles that have the exact same mass. If you charge up one of these particles, like let's say an electron, which is of course always charged, or let's say an ion, an atom that has been ionized, then you get a unique number for the charge to mass ratio, which can be used to identify a particle. And we're going to see how this is done very shortly. So let's do an example now, and then we'll get on to a neat technology. Sorry, here is the example. Okay, so this is sample problem 1. It's in your physics textbook, Physics 12 by Nelson. And they say, an electron accelerates from rest in an electric field through a potential difference of 46 volts. The electron then leaves the electric field and enters a magnetic field of magnitude 0.2 Tesla directed into the page. Now, I got to warn you, there are two things going on in this problem, and we have to separate them. The first part, which I'm going to underline so that you can see what it is, the electron accelerating through an electric field where the potential difference is 46 volts. If you forgot section 7.6 in your textbook, you've got to go back there. Remember the motion of charges in an electric field? That's what this part is about. What they're trying to do is get you to figure out how fast the electron's going to be moving, because then it's going to leave the electric field and it's going to enter a magnetic field, which I'm going to underline right there in red. Okay, so this is what we are learning right now. Learning now, that doesn't look like the word learning, does it? This is what we're learning now, but before we can do this, we got to do this calculation for the speed of the particle first. So if you forgot this, please go back and refresh your memory. Look back in your notes or look in this section. However, the idea is as follows. Do you recall from section 7.6, the law of conservation of energy, which told us that the change in electrical potential energy is equal to the change in kinetic energy, although with a minus sign in there, because if one type of energy goes down, the other one goes up by the same amount. How do we calculate electric potential energy? We use Q times the potential difference. And of course, this will be EK final minus EK initial. It says the electron accelerates from rest, so I know that's going to be 0 there. And what else do I know? The charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. And when an electron is accelerated, it's because it is going toward the positive plates. So, for example, if you had oppositely charged parallel plates, one side negative, the other side positive, an electron would be accelerated to the positive plate. So it would go from a negative or low potential to a positive or high potential. That means that the change in potential would be from a low number to a high number. That'd be a positive value. So we put in here plus 46 volts. Here we've got negative EK final, which is negative a half. The mass of an electron, which is 9.11, 10 to the negative 31, and I've run out of room here, so well, maybe I can squeeze that in. Let's see. I could probably, there we go, V final squared. And if you take a moment to solve for V final, what you're going to know is the final speed of the electron when it exits the electric field and finally gets into the magnetic field, which is the part that we're learning now. So let me just pause the video here and make sure that I get the right calculation. You can do the calculation as okay, so I've got a value of the final speed of the electron being 4.0197 and a whole bunch of other digits times 10 to the 6 meters per second. So this is the speed with which the electron will enter the magnetic field. And just to give you a visual representation of what's going on, imagine a magnetic field like we had here, and a particle entering it, such as in this position. It's moving with a speed v. The direction we'll look at in a moment. the magnetic field and the speed are going to, according to our new formula, exert a force which is perpendicular. We know it's perpendicular because of the right-hand rule, and that's going to lead to uniform circular motion like we discussed just a moment ago. So what do we do now? It says the electron now leaves the electric field, enters a magnetic field directed into the page. Now, we got to worry about directions here because this is a vector problem. So what did it say? The electron was accelerating into a horizontally directed electric field. So let's see here. The electron leaves the electric field, enters a magnetic field, which is directed into the page. So what I'm going to do is draw that magnetic field into the page. And how do we do that? We use X's like this. Now, because the electric field was directed horizontally, my diagram up here did reflect that. Remember, the electric field is defined as the direction of force per unit charge on a positive test charge. So the electric field is actually directed to the left here. That would be the fancy E symbol. Because the electron was negative, it went to the right. However, what I can do now is draw the velocity of that electron as being this way. So there's V, here's the electron. The magnetic field is into the page like this. And what I want you to do now is do right-hand rule number 3, where your fingers will be in the direction of the magnetic field, which will be into the page. Your thumb will be in the direction of velocity, and therefore your palm will be the direction of the force. However, very important here, you're going to have to realize this is an electron, and the formula we use for the right-hand rule involves positive charge. So you're going to have to reverse the direction when you are determining the direction of the force. So what do you get here? I've got my fingers pointing toward the computer screen. I've got my thumb pointing to the right, but then I turn it around to the left because it's an electron, and I get a downward force on this electron. So let's draw that in here. A force going down like this, which is perpendicular to the velocity, and that's going to cause the electron to curve in what I would describe, which I should draw that in black because that's the direction of the velocity, going to curve this way in what I would describe as a clockwise circle. There will be some radius to that circle, and I believe that's what they ask you to calculate here in part C. So let's continue with this calculation. We start by saying that the magnetic force equals the centripetal force. QVB sine theta equals mv squared over r. And we notice that the v there and one of the v's there is going to cancel. Theta is going to be 90 degrees. So maybe I'll put that in right away because sine theta will be 1. So what have I got here? Let's isolate r. R equals mv over qb. Now the mass of the electron, 9.11, 10 to the negative 31. The velocity is this number here. Warning, it is not the voltage. I would guess about 50% of students make the following mistake. They see the letter V, they see the letter V here. They're not always paying attention to their symbols, and so they sub them in. That's why you have to write V speed as little v and big V as voltage. If you don't respect your symbols, they have a way of tricking you and giving you the wrong answer. The V here is speed. The V there was voltage, which may have helped the electron gain its speed, but they are not the same. Divide by the charge on an electron, 1.6 by 10 to the negative 19 coulombs, multiply by the 0.2 Tesla magnetic field, and what do you get? I'm going to do this calculation. You can do the same. Okay, folks, and the number that I got is about 1.14 with a bunch of extra digits times 10 to the negative 4 meters. So just about 1/10 of a millimeter is the radius here, which is a pretty small radius. However, the magnetic field is quite strong, and the speed of this particle, while it seems high, is not very high compared to, say, the speed of light, which is kind of like the standard for very fast-moving particles. We often compare them to the speed of light. So it's understandable that this electron makes a pretty tight circle. All right? Now, what I've just described to you actually forms the basis of a very important piece of machinery in the study of science, and especially the study of chemicals and identifying particles. The piece of machinery or the piece of technology that I'm thinking of is called a mass spectrometer. Let me explain. Here's a diagram that I found on Google Images, and I'd like you to follow along here. We start off by taking a sample of some substance. This could be a sample that you're trying to identify. Let's say if you were a crime researcher, maybe you would take a sample of, let's say, something you thought that was gunpowder, or a chemical from a bomb, for example, or maybe it's a substance that you're trying to identify. You're a chemist working in a lab and you want to know about the particle. Whatever the case may be, the sample is inserted at one end of this machine called a mass spectrometer. It is ionized usually by heating, and then the ions, so these are molecules that have become charged, they are accelerated to a certain speed. And the way they're accelerated is very similar to what was just described here. They are passed through an electric field. So that was the first part of the sample problem. Next up, the particles start moving. They are now ions, so there's a beam of ions, and they enter a magnetic field, which, as you can see here, is probably directed, it could be directed in the up-down direction, or it could be directed in the direction of coming towards us out of the page or away from us into the page. I'm just going to take a guess here. I'm going to guess that the magnetic field here is up or down, and I'll see if you can guess why in a moment. As you can see, the ion beam suddenly takes a curved path, and they show three possible curves. One curve is kind of right down the middle, which goes into a detector. One curve is too tight and it crashes into the side of the machine, and one curve is not tight enough and it also hits the outer wall of the machine. Now, let's see, if you have your right hand and your thumb is pointing this way in the direction of motion of the ion beam, and your fingers are pointed down or up, either way, then your palm will be facing either into the page or out of the page toward you. That's what's going to cause these particles to curve this way toward our faces. I guess you would need this force. You could not have that force. That would send them curving the other way, like that, into the page. So the reason we can't tell exactly whether the magnetic field is up or down is because we don't know whether these ions are positive or negative. So in all likelihood, they ionize the sample, they get the beam of ions, and then they direct, the researcher that is, would direct the magnetic field up or down in order to get a force that causes a curve toward the detector. And basically, you have to adjust the magnetic field until the particles enter the detector. When that happens, you will know through ionization they are charged, so we have Q, and we're going to know the radius because, of course, only one radius of curvature can get the particles to go into the detector. We're going to know the magnetic field because we have a device that sets that magnetic field. And so from this, what are we going to find out about the particle? Well, let's go back to our physics, which was over here. Remember this, R equals mv over qb. Well, I know R, I know Q, I know B. So the neat thing here is I can figure out M if only I knew how to find the speed of the particles. Well, how do you find the speed of the particles? Well, there are two ways. Here's the easier way that I'm sure you'll recognize right off the bat. Remember in this part where I said that the ions are accelerated forward so that they begin moving into the magnetic field? That is just like what we did over here. It involves this calculation. All right? So if you can figure out how fast the particles were moving, you just take that V, you sub it in here, and all of a sudden you know this. So what are you going to find? You're going to identify the mass of these ions. And remember what I said to you a while back. Ions, which are chemicals which have gained or lost an electron or two or three or whatever the case may be, they have very unique masses. I mean, there's not too many things that can have the exact same mass when we're talking about particles. Think of, let's say, a nitrate ion. Maybe you are a crime scene investigator trying to determine whether this chemical is present where there was an explosion, let's say. Well, what are some of the possibilities? Maybe nitrate ion would be there. Maybe, I think that's sulfate ion. I think it was 3-. You'll have to ask the chemistry teachers. It's been a while since I did that. Maybe it would be sulfate. SO4, I think, was 2-. Each of these ions has a unique mass, and therefore, they're all going to take different radius paths. So only a certain ion can enter the ion detector based on how you set the magnetic field. By doing all of these calculations, we can identify the mass of the ions. We can identify what's in the sample. And this could involve, let's say, maybe you had a blood sample and you were trying to identify whether certain chemicals were in someone's blood. I imagine you could do this kind of investigation. If you really want to get a good idea of how this works, go to this YouTube video, mass spectrometry, MS, and watch what they do in here. It's really, really cool. It's about 7 minutes long. Definitely worth checking out. All right, one last thing. I was talking in here about one way to find the speed of the ion as it enters the magnetic field. There is another way which is described in your book, and that is using something called a velocity selector. This gets a little bit tricky, so pay attention. You're still going to use a potential difference to accelerate the ions and be able to use this formula. However, instead of using this, consider this argument. The ions get moving in the forward direction accelerated by the large potential difference over here. And now what we do is we have some coils, and if you recall, when we were learning about a solenoid, remember this from the grade 11, grade 12 video, we learned how a coil, if you use right-hand rule number 2, it's got a magnetic field, which for example might put a north end here and a south end there. That would work if the current was flowing up this side and down the back. All right? So what you do is you take some coiled wires and you generate a magnetic field in them by connecting them to a power supply. In this particular setup, the coil is oriented such that your right hand would either have its thumb pointed toward you or away from you, depending on how the current is flowing. They show you the current flowing this way. So take your right hand, put your fingers in the direction of the current here, and now your thumb should be pointing into the page. So that's the magnetic field there. Now another thing you can see in this diagram, I'll just zoom in to make it more obvious, and then you can check in your book to see a neater diagram. You see these parallel plates here. They're in orange, right? Right up here is one, and there's another. They are connected to a power supply, and of course they are going to create an electric field that is either down or it could be up. They don't tell us right now. However, if you remember from section 7.6, where we studied projectile motion and particles, the deflection of charged particles in an electric field, this will lead to a force, an electric force, that is either up or down. We don't know which because we don't know how these have been connected to a power supply. At the same time, you've got your ions which are moving in this direction, as I've shown. So that is their velocity. And they've entered a magnetic field that we've described as into the page. So taking your right hand with your fingers into the page and your thumb pointing to the right, your palm will be up. Or if it's a negatively charged particle, your palm will be down. That'll be the magnetic force. So here's what we do in this device called a velocity selector. We take the ions and we fire them through this combined coil and parallel plate apparatus. And we set up everything so that the magnetic force is pointing one way on our charged particle, and the electric force is pointing the other way. And we adjust the two until these are equal, so that Fm is equal to Fe, so that QVB, sine of 90 degrees, I'm going to leave that out, equals QE. The charges cancel. The speed is then equal to the ratio of the electric field to the magnetic field. The idea being, if you can get a beam of particles to travel straight through this device here, that will mean that the forces of magnetism and electricity are balanced, and the speed will be exactly equal to the electric field in newtons per coulomb divided by the magnetic field in Tesla. You will know precisely the speed, and then you'll go back to this calculation over here and you'll sub in for speed. This is just another way of finding the speed using the velocity selector method. Of course, you can also do it the way we did in this calculation here, using the law of conservation of energy method. All right, I know that this is a little bit tricky. You'll have to kind of think about it. You may have to pause the video and just sit there and think for a moment, but I hope you've enjoyed the presentation. The mass spectrometer is a really cool instrument. Watch this video. It'll show you one in action, and I bet you by the time you get to third year undergrad chem or physics and probably bio as well, you'll also use one. All right, folks, thanks for watching, and I'll see you in class. Take care.